Good evening, everybody. So glad to see you all here this evening. We have Dr. Meeks here tonight from the U.S. Geological Survey to talk to us about bedrock geology and what it means regarding our drinking water. And just to give you a little background, Jessica actually has quite a background in the topic. She got her degree at the University of the Neuchâtel in Switzerland, where she assessed and modeled the impacts of climate change on groundwater removal. And I think that's right what we're here to talk about tonight. Her research was done in regard to a United Nations project at the time. And Jessica also serves on the faculty of the University of Maine School of Earth and Climate Sciences. And as Jessica mentioned, topography matters, and I think Jessica's going to help us learn why and how our topography is going to affect our groundwater. So just as a side note, before I turn this over to Jessica, we've getting a number of questions. You know, what normally happens, you start to set up a program like 6 months ahead of time. And then inevitably, some emergency happens the week that you're doing the program. And of course, that was the PFAS spill in Brunswick, which is on everybody's mind, I'm sure. I just wanted to mention, though, tonight, the focus of tonight's program is going to be on the fractured rock aquifer, because that is what we are prepared to talk about and what the science is behind. And we ask that in the question and answer at the end, that the questions relate to that topic. I can mention that as of Monday, the town has updated the town website, and you can go there. It's at the town, and it's under Forever Chemicals. And they have all the information that's the most up-to-date from regarding that spill. So if you have questions on that, that's going to be updated. You will get your most current information at that site through the town. And I just invite you to go there for more information on that. So with that, Jessica, I'll turn this over to you. Thank you.
Thank you for coming. This is quite the turnout. Sometimes, like when we have a town engagement, there might be 4 people, 12 people, and I think we're in the 100+ range here tonight. So as mentioned, I'm a hydrogeologist with the Maine Geological Survey. And at the Maine Survey, we are a non-regulatory body of the state government. What we do, we serve as experts on our subject matters. We have a bedrock geologist, a surficial geologist, we have coastal and marine geologists, and we serve as a resource for other departments and for constituents around the state on whatever the given earth science topic is that you would like to have addressed. And so I'm a hydrogeologist, and my background spans everything from karst hydrology, which is caves, to snow hydrology. I'm the person in charge of the snow survey for the state, the New England Snow Survey. If you've heard of that, that's my baby too. And I have been with the survey just for the past year. So prior to me coming on board with the survey, we really didn't have the resources at the survey to look into saltwater intrusion in coastal environments. And it wasn't as much of a concern a number of years back. But now that's come more and more to the surface. And so this is a mutually beneficial meeting here, in that one of my objectives for connecting with communities is to help identify wells that are out there that we might be able to use for monitoring down the road. And I'll touch on that later in my talk, but just to kind of plant that seed. So thanks for coming. And also, since this is a community engagement, I'm assuming you're coming from a broad swath of backgrounds. And so to start with, I'm going to just be covering basic hydrogeology and really what the geology is of Harpswell, so that we're all on the same playing field and we all have the same vocabulary. And when I say water table, you know what I'm talking about, and then your neighbors know what you're talking about. And so we're all on the same page. So to start with, we have the water cycle here. We have precipitation that falls down. And then we have losses that go back up to the atmosphere as evaporation, transpiration, which is the off-gassing from plants, and sublimation, which is the vaporization of water from snowpack. And then we have infiltration, and that's the water that actually enters the subsurface. And then we have surface runoff. Okay, so those are the main components of the water cycle. And what we have here is a kind of idealized cross-section of what the land surface might look like. So precipitation falls, it passes down through the vadose zone, which is the unsaturated zone, vertically with the gravity. And then once it hits a point where all the pore spaces or fracture lines are completely saturated with water, that's when you entered the groundwater. And that interface between unsaturated pore space and saturated pore space, that's the water table. Okay, and that goes up and down with time depending on the inputs and the withdrawals. It's like an economic water balance. Okay. And so when water hits the water table, it then will flow in the general direction of high elevation to low elevation. So we'll follow the potential energy, and usually that mimics the surface topography. And I touched on this with one of the people out here, usually, not always, but at the regional scale, definitely. Okay, so not all groundwater is actually part of an aquifer. An aquifer is an actual term that's used to define a water-bearing geologic formation. So it's a geologic rock that has enough porosity in it, cracks, fissures, pore spaces, whatever, that can hold water that's of a usable volume for a groundwater well. Okay, so groundwater and aquifer are two separate terms, and an aquifer is usable water. Does that make sense? Yeah. Okay. Similarly, you can have a groundwater, a rock body that has a lot of pore space in it that can hold a lot of water, and it might not be an aquifer because the water doesn't come out easily. So like if you live in parts of central coastal Maine, there's something called the Presumpscot Formation, which is principally made up of clay. Clay has a high water holding capacity, up to 50% of its volume can be water. But clay has the ability to bind water molecules to the actual clay particles. And so the water gets kind of trapped in there and the water doesn't come out easily. So you can have a high water holding capacity, but a low permeability, which is the ability of water to flow through. And similarly to clay, if you have like a granite or something that has fractures in it, but those fractures are not connected, the water won't flow through the rock system very readily. Is that kind of aligned? Yeah, okay. So there are principally two types of aquifers here in the state of Maine. And the first one I'm going to touch on is sand and gravel aquifers. And those were left as depositional units from the retreat of the last glacier, principally. And so for mapping purposes, the state is broken up into grids that are called quads or quadrangles. And what we have here are three of the grids. And the mapped significant sand and gravel aquifers in your vicinity. And sand and gravel aquifers kind of look like this idealized, cobbles and sand, and water can pass through the pore spaces in between those grains pretty readily. And what makes it a significant, the word significant is significant, a significant sand and gravel aquifer is that you can withdraw 10 gallons per minute at a sustained rate from that well. So two types of aquifers, the first being sand and gravel aquifers, okay? And those are depositional units that were left behind during the last glacial retreat. And those are marked by the yellow and orange that you see here on the map. And they are considered significant because they can yield greater than 10 gallons per minute at a sustained rate from those units. But so why do we not have a map for Harpswell? That's suspicious omission here. So my predecessors at the Maine survey went out and they did not map any significant sand and gravel aquifers on South Harpswell, Bailey Island, or Orr's Island quadrangles. So unfortunately, you are not blessed with one of these high yield units. There may be small segments of sand and gravel deposition around Harpswell, but they have not been identified. So if on your lot you happen to say, oh, well, we have some here. You know, maybe that's just something that wasn't tapped into during that historic mapping event. So what other superficial geology do we have on this area if we don't have significant sand and gravel deposits? In 1985, there was a comprehensive map done at a coarser scale that just identified a thin drift. So that just means a thin deposit of glacial debris left behind. And most of you can corroborate this by all the exposed bedrock that you probably see around your properties, right? So we do have a superficial geologist working on creating a finer resolution superficial maps around the state, but she has not made it to this section of the state. She is one person covering the entire state of Maine and covers one quadrangle, maybe two a summer, because there's so much to get into. So that's something to look forward to down the line, and it is kind of up on her list. So in the next few years, I think she will get to this area, which should be illuminating. Okay. That said, Harpswell is likely to have similar superficial deposits to the Freeport quadrangle, which is just west of here, with types of shoreline deposits, some Presumpscot formation, which is that clay that I mentioned earlier, and some till and some thin drift areas. And so underneath these superficial geology layers, you principally have two kind of categories of bedrock. You have the Cape Elizabeth formation and its kind of close cousins. And then you also have the, I can never say this name, Sebasco. Thank you, formation. So thank you. So both of these groups are metamorphosed sedimentary rocks. And so they were originally sediments that were deposited in an ancient sea. And then those sediments got compacted and lithified, which means they turned into bedrock. And then there was a tectonic event where the sea closed up and we had a collision of plates, and those sediments got compressed and tilted and folded and cracked. And that's how we ended up with the bedrock that we have today. So we have old metamorphosed sedimentary layers lying around this part of Maine's coast. And during that tectonic event where the plates collided and caused all this folding, that's when a lot of the dominant fractures and faults and fold patterns are that you can see when you're walking along the coast and whatnot. And you can see on the picture on your right, it's actually layers that have been folded over like this and the top has been sheared off. Okay, so think about if you had a stack of paper and you compressed from both sides, you'd get rumples, and then with erosion, you cut off the top, and that's what you have at a site like that. Okay, so if you're interested in the dominant fracture patterns around your area or the greater state of Maine, you can go to the 24K bedrock map that's on our website at the Maine Survey. And you can look for these strike and dip directions, and that'll show you the kind of the orientation and the angle that the dominant fracture patterns are for your area. So why am I getting into the geology in such detail? This is really just setting the stage for your water resources, the holding material for your water resources. Harpswell residents get all their usable water from groundwater wells that happen to tap into one or more water-bearing fractures. Water-bearing being operable, right? If you have a fracture with no water in it, it's useless to you. And while there is a dominant trend, as is shown in that last map of the fracture orientation and their dip, there is a dominant trend. It is pretty impossible to know the exact depth of the fractures, the distribution of the fractures, how many fractures, do you have one or seven, a cluster of them? How interconnected are they? You really don't know that until you go in and install a well. So this is what a general bedrock well will look like. What they do on the picture on your left, you see a drilled bedrock well, and there's casing that extends down into the bedrock. And then below the casing is just an open hole in the ground. And so the drillers will go down and they'll drill until they've encountered enough fractures that are dripping out water that they feel like they're going to generate a significant enough volume of water that's going to serve your property, whatever it may be. And so the image on the right is a more detailed image that shows a submersible pump, which is where the water gets sucked out of, and then it gets routed up and passed through a pitless adapter over to your home. That's generally how it is configured. So now that we've talked about kind of the lay of the land, literally, I'm going to get into saltwater intrusion a bit. So what happens when freshwater meets saline water? So here is an image of the Fraser River, which is in the Strait of Georgia in Vancouver, BC. And you have, too far. This is where fresh water that's full of silt, that's the foggy colored water, meets the clear blue ocean water. Okay, and it looks like the bodies of water are not mixing. And so if you were to kind of envision what it would look like in the subsurface, you might kind of think it looks like this. You have fresh water, salt water, and they're just kind of going along next to each other. But that's not actually the case. Fresh water rises up over the denser salt water to create a slanted mixing zone under the surface where the mixing of the two waters occurs. And here in Maine, our coast looks something like this, where you have a rock that hosts the aquifer, which is in direct contact with the ocean. And the fresh groundwater from higher elevations comes down to the lower elevations with gravity to the base level, which is the ocean. And then the mixing of the two waters does not occur out in the ocean. It actually occurs beneath the rock in the aquifer, below the aquifer. And this is a result of density differences between freshwater and saltwater. So the saltwater is denser, so it actually intrudes into the rock formation as a lens that extends underground into the land surface. That transition zone, or that mixing zone between freshwater and saltwater is called the zone of dispersion or the transition zone. And that's where most of the chemical mixing occurs between the two types of water, because they have very different chemical profiles, and the constituents that are dissolved in them can be totally different, as was evidenced by that Fraser River photo. So not Maine. Places like the Barrier Islands, the Carolinas, Cape Cod, where most of the saltwater intrusion studies historically have taken place, were in these sandy, nice, uniform settings. And what's beautiful about that for them is that when the transition zone moves inward, it does so in kind of a uniform way. And it's called homogeneous and isotropic movement of water through this parent material. Unfortunately, that's not the case for us, because we here in Maine have fractured bedrock. So these fractures in the joints, they fully control the transport of groundwater and are variable in density and the thickness and the interconnection. And this means that the rate and the spatial distribution of the migration of that transition zone is not this nice front moving inward. It kind of snakes its way along the connected fracture zones. So it's really, really, really difficult to predict exactly how that saltwater mixing zone is going to migrate through the subsurface, because we just can't see into the ground in an ideal way. Saltwater finds its way to a well via a single fracture in this graphic, okay? But you can have a neighbor go in and put a well 200 feet away, drill it down to the same depth, and they might not hit that same fracture that happens to be connected to the transition zone, and they might only be connected to some other fracture zones that are not interconnected with the saltwater. So really putting in a well, there's a gamble to it of like where you're going to hit on this interconnection. And this is the heterogeneous nature of fractured bedrock. And that just means it's not the same everywhere you go, and that water moves at different rates, in different directions, depending on kind of what the fractures are doing. And just really implies that modeling and predicting in Maine's bedrock is incredibly complicated. So this transition zone is not static, even without human influence. So if you take humans completely out of the picture, this transition zone is still going to be moving around. So in late summer, when you have evapotranspiration is high and precipitation is typically low, you're going to have less water infiltrating into the ground, which is limiting the freshwater's ability to kind of essentially push out on the transition zone and keep that salt water at bay. And then in late winter, early spring, when you have no leaves out, so you have no no transpiration, lower evaporation, and you tend to have a lot of precipitation in the spring, so you have more water entering the ground surface and more pressure pushing that transition zone at bay. So the whole freshwater lens that's under island communities and peninsular communities actually pulsates seasonally, which is pretty cool. There's also a tidal influence on the transition zone. And this is my colleague, Ryan Gordon, who's now the head geologist at the survey. And he's the other hydrogeologist who's been with us for, I don't know, 8-10 years or something like this. But we have a monitoring station out on Allen Island that's owned by Colby. And they have allowed us to instrument a well out at this site. And the monitor that we put down over the last year has been measuring conductivity of the water. And so you can see from this orange straight line at the beginning that it's fresh water. It's nice, clean, fresh water. It's a little bit salty, but it's potable. And then you see it dip down and go back up. The reason it dips down and goes back up slowly is because there was a rain event, and atmospheric water is has an even lower electrical conductivity than groundwater. So what you're seeing there is a pulse of influxing rainwater into the groundwater body. And then when you look at the blue line, you see this going up and down. That's actually the tidal flux. So when you map the tidal cycles on top of this, they're very coincidental. So what you see here is proof that the freshwater lens, so the monitoring device was in the freshwater lens, it was not in the transition zone. The freshwater lens is going like this twice a day with the tides. So it's ultimately influenced by the lunar cycles as well, which is also pretty cool. And at the so some other notes. The greater the tidal amplitude, the greater amount of mixing that you have at the transition zone. Because if you think about the amplitude of a tide, if you have a small tide, you only have kind of this much variation of force that's being pushed into the subsurface of the ground. But if you have a greater tide, you have a greater amplitude, a greater force in a shorter period that's kind of causing mixing along that pathway. So there were some hydrogeologists a number of years ago that observed that there is this freshwater lens that kind of perches on top of salt water. And they noted that for every foot above sea level that they found the water table, it seemed that there was 40 feet of fresh water below that. So that's this principle here. And really what that means is that if you have, for example, 3 feet if your water table is 3 feet above sea level, you'll have 120 feet below sea level of fresh water. And when you add those up, you have 123 feet in theory of fresh water sitting above that saline transition zone. So you can kind of gauge how much water you should have below you by how high your water table is above sea level. And again, this is a principle that plus or minus, it's not a hard rule, but within that range, you should find. So this is meant to be a little bit of a joke because it's a little overwhelming, all the things that we have kind of to work with. But so ultimately we have a lot more people and we have warmer temperatures than we did 50, 100, whatever years ago. So those are kind of our two dominant challenges. But before we get into those, I will want to note that some good news. This is a well that's monitored and hosted by the USGS up in Brunswick. And they've been monitoring this well back the late 50s. And these blue circles are the depth to water. And you can see that there's a clear trend moving upward. And so what this shows is that the depth to water is getting shallower. And since we know that there aren't fewer people here since the 60s, and people are generally using more water now than they used to, it stands to reason that that increase or decrease in depths of water is a result of increase in precipitation. So we actually have more water falling on us now than we used to, and that's showing up in our water records, which is really interesting. So we have more than we used to, which is great. But so projected impacts from sea level rise. So sea levels kind of come up. So we have inundation, which is the coast kind of eking inland. And then we have intrusion, which is that transition zone eking inland also. And so with sea level rise, it's expected that both of those things will occur. And so I don't know if this is gonna, the Nature Conservancy has done this really cool, created this really cool map, but we zoom in. And you can open this up and you can play around with it. It's quite interesting. And you can look at what sea level will do at 2 foot rise, 3.3 feet, 6 feet, and you can see all the different scenarios of inundation. And then you can also, they have another map somewhere on here that'll show, it'll actually show like what roads will be inundated at different sea level rises, what homes will be impacted at different sea level rises. So that's an interesting thing if you want to go check out later on. Also, if we have more people drawing on our aquifers, what happens then? So all these images are not to scale at all. But in this first image, we have kind of this idealized non-pumping well in an unconfined aquifer at equilibrium conditions. So that means that the well is not pumping, clearly. Unconfined means that all the infiltrating water will reach the aquifer. There's no layer, geologic layer in the middle somewhere that's going to block that water from reaching the aquifer. And equilibrium conditions just means that humans aren't interfering yet. So what happens when we start pumping a little bit? Well, you'll have two things happen. You have a cone of depression that will form at the top of the water table, and that's the kind of divot in the water table. And that's implying that the water is getting drawn down around it. And then you also see at the transition zone, an inverted cone of depression where the water is getting sucked up. So at this point, the person's pumping, but they're not pumping enough to really impact that transition zone. And so they're still drawing in fresh water. And if they intermittently pump, they should be fine. But if you keep drawing on that well and go hog wild with it, you're going to suck the transition zone up into your well screen, and then you'll start having briny or saline water. So these are kind of exaggerated photos. Really what it would look like is more kind of this gradual inundation like this, like a more swing of the transition zone than this big dramatic cone. But I just did that for graphical purposes. So I looked at one well. What happens when you add a lot of wells together? So the main water well database is run by somebody in my group, and what we have here are all the registered wells, and this is a fraction of the actual wells that exist out in the landscape, because the regulation for the Maine Water Well Commission to have the Maine drillers submit information to the state only happened in the latter part of the last century. And so all the wells that were installed prior to that, we don't have data on that. And it is a requirement now for the drillers to submit well data to us. We have no authority to penalize them if they choose to not submit that to us. So it's kind of an honor system. And I'm now going to be starting the process of calling up the drillers and saying, hey, remember us? You're supposed to be submitting our information. We haven't gotten anything from you in a little bit. So what you see here is just a fraction of what is actually out there. So it's just a lot of factors to consider on the draws on our water. I've had people in the past ask about, what about population distribution and shifts in time? And the 2020 census was saying that Maine is projected to have a decrease in population over the next couple of decades. However, there have been some studies that have also said that the census doesn't accurately or adequately account for for climate-induced migration of people. So I'm not an expert in this area, but it's something to consider. And the Gulf of Maine Research Institute did put together a very interesting 4-part speaker series. If you wanted to go check that out, you can just look up climate migration, GMRI, and you'll find it pretty readily. So if you suspect that you have salty water, what do? You need to go test it. There are a few ways to do this. You can look at the total dissolved solids, that's TDS. And this is referring to the collection of solutes that basically you have mixed in your water. And so the fewer solutes, the softer your water. And I think most people probably have heard of soft or hard water. I feel like that's pretty common terminology. And if you look way over on the right is salt water. So you want to stay away from that if possible. Another way of measuring salinity in your water is looking at the electrical conductivity of the water. The more solutes you have dissolved and floating around in there, the more current is readily going to be passed through that water. And so the higher the solute content, the higher the electrical conductivity. It's kind of a direct relationship there. And so just to note that sodium chloride is not the only thing that's floating around in your water. You have a whole host of different compounds and minerals. And so when you're looking at salinity, you're kind of looking at the soup of it, not just sodium chloride. So how does my group fit in with all of this? I get questions pretty regularly of, is saltwater intrusion occurring? If so, where? And how will sea level rise accelerate, exacerbate saltwater intrusion? Can my coastal community support more people coming in here and putting in more wells? How do we stop development because it's going to cause saltwater intrusion? I get comments like this pretty commonly. And my honest answer is we don't have a solid grasp on what's happening along the coast because we just don't have the data. And so that's my plea to you all, is that if you have or know of a groundwater well that is not contaminated, that is not being used, and that you'd be willing to have instrumented, I would appreciate you reaching out to me, and then we can see if it's a good fit for our program, because we've received, or we will be receiving money from a coastal resiliency grant that is allowing us to purchase equipment to instrument wells up and down the coast. So this is something that's very active program for us, but we don't have the funds to actually install the wells. So that's why I'm looking for community partnership on this front. So if you have any interest or you know of something that would be appropriate, please reach out to me. But so what will we do, or how will we collect the data? We can either put in one-off samples, just go and collect a grab sample, or we can install continuous monitoring. Some of the systems are telemetry systems, which actually transmit data in real time via satellites. And then what do we do with that data? Well, the survey has a very established pattern on this front where we've collected snow water equivalent data across the state, and we've taken that and we've created maps and looking at snow depth as it transpires through the season. And so we could do something similar to that, or we could follow what the CDC, the state CDC does, and aggregates data by county or by town and then produces maps in that way. So we would like to collect data in a way that is useful for the community while also protecting individual property owners' privacy. So that's my groundwater monitoring well plea, and move on from that. So saltwater intrusion adaptation strategies. So I've been at this role about a year, and I've only been on this kind of saltwater intrusion stuff for the last few months. And British Columbia has been on this for years. They have their ducks in a row and have done an excellent job of creating literature and management strategies. And I won't read through all of these. And this presentation, I think, will be made available if anybody would like it down the line. But I think the principal component is the third one. Practice water conservation. That first 3 words there. So when we're looking at the Harpswell community, generally around this area of Maine, you get about 46 inches of precipitation a year. About 50% is lost to runoff. So that's just fluffing off the surface and going into your surface water bodies, rivers, the ocean. 30 to 40% of that is lost to evapotranspiration, never even really goes into the ground. And so we're left with about 7 inches of precipitation to actually replenish our aquifers. The average person uses about 55 gallons a day in the US. And so multiply that by the numbers of days and residents that we have here in Harpswell, and this is 100,000. That's a lot of gallons, right? That's being used. When you look at the infiltration of the potential infiltration of Harpswell versus what's actually being probably used by the residents, there's still more water than is being used, which is great. That's how you want it, right? But I think that there's a big asterisk to that, because when you look at the population distribution along the peninsulas, they are not uniform. You have big clusters in certain areas. And so those areas are going to be harder hit and are going to need to conserve water more than if somebody has 10 acres kind of up in the northern part of the peninsula where it's wider. And that's just the reality of it. So water conservation is key. And so I'm going to wrap up the talk with some questions that were presented before, and just kind of go through and answer those. So somebody asked about the wells, and really what I can say is if you have private well information that you find to not be in our database, feel free to reach out to me and share that data, because I can have that loaded into our system and to bolster that. And then the second question is, how do we evaluate or calculate if volume of water used is mining groundwater or is imbalanced with nature's recharge in the bedrock aquifer? So my first thing I would say is monitor your use. You can put a meter on your pump to see how much water you're actually using. You can monitor the quality of your water. If you see an increase in dissolved solids or the total dissolved solids in your water, something's happening there. And then you can also go in and you can make a simple water balance for your slice of the community. So like in this little slot that I selected for no particular reason, like you could count up the number of homes and how many people are there, and you could come up with an approximate volume of water that's being used by people, and you can back calculate just in the same way that I did how much water is being used. And does this make sense? Should we, as a small little micro community of Harpswell, up our efforts to work on water conservation? Another person asked about the spill, the PFAS. I'm not going to get into PFAS. I do have a background in PFAS if there's some general questions, but I don't know the nuances of what the PFAS program has been doing, because that is not my domain within the state. So I am not up to speed on what's happening there. I just don't know. But I will say that generally speaking, water follows the topographic gradient, generally speaking, and a regional scale, okay? If you live on, all these peninsulas have ridges along the center of them at some point, right? A point of high elevation. If you live on one side of that ridgeline, the water is going to generally flow down that side in the subsurface. If you live on the other side, it's generally going to flow down the other side. So that's kind of an overarching flow pattern that you'll see in the peninsular communities. You're not going to see water from North Harpswell following down the spine and showing up in West Harpswell. That is not hydrologically possible. You won't see that. So what's happening up north is to some degree independent of what's happening in the middle and down south. I would look at it from a band across the peninsulas if you're trying to kind of figure out what's happening in your little hydrologic world. And also when you start pumping, this is what it kind of looks like. You'll see this cone of depression. So one of the questions was, what's my impact? Like what's my protection area around my well? Well, generally it's around 100 feet from the well is what's advised, to make sure that's clear of potential contaminants. Like you don't want to dump paint remnants 2 feet away from your wellhead. That's a bad idea. But the cone of the radius of the cone of depression is really the lateral area that the water is drawing from. So if you're beyond the cone of depression of that, and you can find this with a hydrologic test, a pump test. If you're beyond that, you're kind of outside that influence zone. And so the last question was, as a private well owner in Harpswell, who's responsible for protecting my water source? And it is you folks. It is the individual you on your property. It is the collective you. I think the amount of people showing up today is incredible. That just shows investment in this topic. And so working together as a community to conserve your water and to really be mindful about your water usage. Running your sprinkler like all day long in the middle of September when there's no rain, maybe that's not the best use of your water. And maybe you talk about that as a community or whatever it is, however you feel like you need to allocate your water, that should be discussed amongst you. But really, at the state level, there is currently, if you have a salt impact from your well, the state will only intervene if you have an arsenic contamination from your bedrock, and that's through the housing authority, or two, if the DOT determines that it was a road salt impact. So those are the only two ways right now that the salt will intervene and put in a water treatment plant or drill a new well if salt has been detected in your well. So barring evidence of either of those things, the onus is on you all to kind of manage your resource and protect it as best you can. And so on that note, I'll leave you with a better image. This is from the eclipse at the top of Sugarloaf. And I'll open it up to questions.
So the recording is going to be shared on Facebook so that you can go back and pick up on the points that you weren't able to hear. So with that, if there's any specific questions.
I do want to add something. I should have said in the as far as source protection, water protection, clearly, if there is a contamination spill, that goes beyond regular conservation efforts. And so that's a big asterisk to that comment, that the state steps in, the federal government steps in, depending on where that contaminant comes from. So I'm talking about beyond that, just general on-property conservation. Go ahead, sorry.
Numbers of people for, and obviously water is a critical component of that solution. I'm wondering, given some of the things that occurred, is there any way to predict how many people we can support in this town? How many residents we can support, given our geography, based on what you know about water system? Is that a limitation that we be concerned with?
I mean, I would say, unfortunately, like this is going back to my quest for wells to put instrumentation in that we don't have enough data to like adequately advise communities on a carrying capacity. Like we just don't have the data on that. So if you're asking if I can say, oh, you can let 5 more people in or 2 more developments, it's like I don't have the information. I don't have the hard science behind that to advise on that. And that's the challenge that we're at right now, which I know is not the answer that you want. I acknowledge that. But it's where we are. And this is one of the challenges that we have, is that people are really tentative about sharing when they've hit salty water on their property. They don't want it getting out. They don't want it being tagged to their lot and tax number. You know, they want that to disappear. And I understand that. That's not great news when you find you have a salty well on your property. And so frequently when drillers do hit salty water, they don't even record it. We get no notice of that. So we just don't have any of the data identifying where there are salty wells, what the concentrations are in those wells. We don't have it, and that's what we're looking to establish. So if there was a program where people felt comfortable sharing that with the state, and we could figure out a way to keep that internal to some degree, like if that was something people were willing to share, that would be amazing. That would be incredible.
That's good to hear, and I think perhaps that's something we can work on, maybe something happens tomorrow. But maybe we can pull something together that would be something that residents give us information about.
That'd be wonderful.
Just had some questions that came in from Zoom. This is gonna knock it. Talking about the availability of drinking water and how the seasonal use, water intrusion, and availability.
So when you have an influx into any community, then it doubles or triples or population, whatever it is here. I don't know what percentage of the population, how it increases in the summer, but you're going to have that percentage increase in your water draws. And so, yes, that will impact what's happening in the aquifers. And as far as seasonal use, you know, if one of the strategies that you can do is, if like watering your garden is an important part of your routine, you can collect runoff in the spring season and fill rain barrels and put those aside and really like create your own storage for water rather than drawing on the aquifer when the demands are higher from the community at large. So there are small things that you can do to help mitigate your personal impact on the higher season. So imagine in this like exaggerated view, if you moved your well, you know, an inch closer to the shoreline, you're going to be in that much more of a narrower part of that lens. So if you can put your well as far away from the coast as possible, keeping in mind you still want it to be further, like at a certain distance from your septic field and any storage like oil storage tanks that you might have on your property, it still needs to keep a distance from those. But if you can move your well inland, that puts you in a thicker part of that freshwater lens. So yes, being at a distance from the coast does help you. Transitioning from no data to some data is a big leap, right? So if we made a prediction now, we'd be basing it on kind of nothing, just anecdotal stories of, oh, my well's been hit. But like if we have some actual hard data, then we'd be able to kind of actually make some predictions based on the observed data. And the more data we have, the better those predictions are. But any modeling effort is always going to be plus or minus some margin of error. And that is just the nature of modeling, that you're taking generalizations about the features of the geology and the features of the aperture of the fractures and what people use for their water. So all of those modeling efforts are always going to be plus or minus some error bar. But the more data we have, the smaller that error bar gets. And it will never be zero. And that needs to be clear. It will never be zero. There will always be some uncertainty in any modeling effort. Like I said, in that like kind of back of the envelope calculation I did, there is more water available than people are using. That said, the distribution of the population density is clustered at the island. So if you just look at a map and you look at one area has a ton of roads on it, and each of those houses has a well, that area is not drawing its water from up north. It's drawing its water just from there. So it's like, you know, certain areas of the islands, yeah, they probably could sustain. I'm not saying, don't quote me on that, but you know, in theory, with the back of the envelope calculation, maybe it would be fine. But in those areas that are tightly congested, that already have a lot of pressure on them. But again, I don't have solid data to support that. So that is all like speculative. If the bulk of the pressure on the aquifers during the summer, when people are using it, you'd want to capture that, right? Like you'd want to capture that heightened stress. But again, if that was the only thing available, then you take what you can get. Yeah, exactly. And really what we need is data over time, see how things are changing. If you need to clean your water so you have potable water, that takes priority, right? Like you need to not be consuming certain minerals. They're not healthy for you. And that's why they advise that you install water treatment systems if you have things like manganese. So if that's the case of your property or your area, you have to deal with that. You don't want to peel away from that. if you reduce your usage on the wells, you can have over time, you can have like a replenishment of the aquifer system. I mean, it shows in kind of some of the graphs that there is a fluctuation to it, right? So you can have, but it's not an immediate thing. Like you turn off your pump and 5 hours later, you're gonna have a thicker rock. You know, you have to have many rain events come in and actually on a larger scale, replenish that area. I'm not a water treatment specialist. That said, you know, you can like a reverse osmosis, usually with a carbon filtration, then a pre-filter carbon filtration, and then an RO system, and then a post-filtration and post-treatment that can add minerals back into the water so that you have a better taste to it. And also you need calcium, magnesium, you need those things in your body. And so if you add them back into your water, you don't have to do it, but a lot of people like it. So generally it's kind of that formula. And the cost and the scale of it depends on whether or not you want to just put a treatment point of treatment under your kitchen sink and just treat one faucet, or you want to do your whole house. And the tricky thing about RO systems is they actually use a lot of water. So usually for every gallon that you consume, there's a gallon of water that's wasted in the treatment process. I lived on a sailboat for a while and drank seawater for 6 weeks one time. You know, reverse osmosis treated seawater. Like you can drink treated seawater. Okay, so you're saying am I saying that water use has increased over time? So generally, from like 70 years ago, yes, people are using more water than they used to. Like over time, people are used more water. They just do. You have more appliances, people wash their clothes more, like they're just habits that have shifted over time. If your unit or your building has a water treatment system in it already, some of them that do have water softeners, you would want to test the water before it goes through the water softener. So, but most of them have like a spigot after or before rather the treatment where you can sample the water. So if you could find where, if there's any treatment in your property and where it is, you can usually sample it before then, and you can, I mean, any lab will analyze a water sample for electrical conductivity or total dissolved solids. So you can always collect the sample there. As far as renters, you can always, if you don't want to, probably not going to want to put a water meter on the unit, but you can buy like water meters for your shower head. There are smaller units that you can install on individual appliances that you can monitor what your water usage is that way too, if that's something that's of interest to you.
We're having another program, October 30th, and it's entitled Precipitation is Our Source of Fresh Water. We're going to be water monitored. We hope to embellish a little bit what we have on the table tonight that talks about ways to save water and how less water in your home. We hope that you join us. We will have flyers out at the time. At this point, I'm not sure where it's going to be located, but we hope you think about coming.